Like other images, the analysis of medical images is guided by very specific expectations. For instance, we may want to detect tumours and characterize their types, or we may want to measure normal or abnormal structures. The certain thing is that when capturing a medical image, there is typically a purpose in mind with regards to its analysis. In this video, we'll discuss different image analysis techniques, which may be used in an automated or semi-automated fashion. Before analysing a medical image, some pre-processing needs to take place to enhance the image. The objective here may be to enhance contrast by reducing any artifacts or noise in the image, or by emphasising differences between objects, for instance, by enhancing edges. So essentially, what we're interested in is to suppress any unwanted information and to enhance wanted information. Feature detection is also often carried out as part of pre-processing, and it may involve edge tracking, corner detection, and template matching, such as blob detection. So why detect such features? Features may help us define a region of interest that will be further inspected, such as lymph nodes. Feature locations and attributes can also serve as references when we want to compare two images of the same object, say before and after treatment. Finally, features may also help to guide segmentation. The purpose of segmentation is to partition an image into different meaningful segments, such as particular organs, different tissue classes or pathologies. This is done by identifying regions of similar attribute, such as similar intensity or texture. In this example, we have an MR image of the brain of a patient with a meningioma, where the meningioma has been segmented. Segmentation strategies combine data knowledge, such as homogeneity of intensity and texture, with domain knowledge about the objects, such as the location of an object within an image, its shape and appearance, as well as its spatial relationships with respect to other objects in the image. Thresholding is the simplest segmentation method, and it can be used to convert a grayscale image into a binary image, that is, black and white. The key to this method is to select the threshold value that determines whether a pixel is classified as foreground or background. Thresholding works particularly well for images where there is a good level of contrast between different structures. On the other hand, it can be sensitive to noise and intensity inhomogeneities, that is, intensity variations or distortions, which typically occur in MR images. Other segmentation techniques include region merging, region growing, watershed transform, and live wire. Let me explain a couple of these further. In region merging, we're not interested in an absolute threshold, but a local variance criterion that is valid for all pixels within a segment. The goal is to separate an image into the smallest number of segments, so that for each of the segments, this criterion is fulfilled. Region growing incorporates domain knowledge, as the user specifies a seed point in an object of interest that needs to be separated. The segmented structure consists of all pixels that can be reached from that point for which a homogeneity criterion applies. Apart from identifying different segments in a medical image, which is the task of segmentation, we may also want to compare or combine different images. This is achieved with the use of image registration. Image registration helps determine a one-to-one mapping between the coordinates in one image and those in another, such that points in the two images that correspond to the same anatomical point are mapped to each other. And when would such a mapping or alignment of images be useful? We may want to compare images captured before and after the treatment of a patient. For instance, to compare the size of a tumour before and after chemotherapy. Or we may be conducting a study with a large patient cohort, where we compare similar images between different subjects. The combination of complementary information from different imaging modalities is also possible through registration. An example is the registration of CT and PET images to combine structural and metabolic information, as shown here. As we have seen in the last few videos, imaging data are extremely valuable, providing an insight into both anatomy and physiology. Imaging data are highly complex, and there are several challenges that the medical imaging community needs to address. Nevertheless, there has been great progress in medical imaging techniques in the last few years. and the community is continuously discovering imaging biomarkers, allowing us to define the imaging phenotype of a disease, leading to improved diagnosis. More importantly, by combining imaging data with other data about the patient, such as genomic or lifestyle data, we can obtain a rich, comprehensive view of the patient, leading to a definitive diagnosis and a focused treatment.